This video has been produced to describe the new network that BT is building for the future. The new network is based on a photonics transmission system. It will be known as BT's ultra broadband network, whilst within Marconi it is known as Genesis. The need for the broadband network. First of all, why build a new network? Quite simply, with the growing demand from customers for increased data speeds and a wider variety of services such as ADSL, Internet and ATM, extreme pressure has been placed on the existing core network. BT needs a cost-effective and flexible solution to these problems and has come up with a new and radical approach to network provision. Why redesign the network? First, let us consider the traditional way in which BT has grown its network. At present, we have a single transmission system using fibres, repeaters and terminal equipment. The typical cost of providing a link of 50 kilometres is between £7,000 and £10,000 per kilometre. So the cost of fibre provision could be up to £500,000 for a 48 fibre cable. To provide greater capacity in the conventional way, for example 10 times what we currently have, we would have to provide multiples of the same system, which would incur costs of fibre provision along with the associated costs for roadworks and civil engineering. Providing capacity in this way would cost around £3.5 million for 10 links and would also require increased space to house the terminal equipment. Alternatively, using modern technologies, we can utilise the same fibre routes to carry increased capacity at lower cost, thus creating a saving in both the use of fibres and in equipment accommodation. As demand for fibre-based services continues to grow, large amounts of investment will be required and the fibre network will still become exhaustive. The provision of new fibre routes will also take a great deal of time. By maximising the fibre usage, this cost can be reduced and the expansion of new services will not be disrupted due to the lack of fibre plants. The new approach to paying for network equipment. Traditionally, BT has provided the complete network system in advance of circuit demands. This means BT carried the whole cost of equipment provision while leaving some equipment not fully utilised until required by customer demand. The new network will be a jointly planned, joint risk venture between BT and Marconi. It will be provided on a pay-as-you-grow basis, with the jointly planned infrastructure being paid for by Marconi, with BT paying as circuits are provided and activated across the network. Close teamwork in developing joint processes and working together to deliver a high-quality network to our customers are critical factors for the new UBB network. The new broadband network. The existing BT network consists of multiple tiers of interconnected SDH rings. Circuits traverse multiple SDH ring layers to achieve an end-to-end connection. This is expensive both in equipment and also in the large number of connections necessary to avoid congestion. To allow direct interconnection at high bit rates, the new design will be provided as an overlay, which will effectively divide the network into two layers. First, the broadband layer. This will be an overlay comprising of just two tiers: collector or inner core, regional or outer core. It will carry VC4s at bit rates from 155 megabits to 10 gigabits per second. In some situations, 400 gigabits will be present on a fibre. The network design is optimised to carry new broadband traffic and is divided into two distinct areas. A collector network or inner core will use DWDM optical systems to form an optical or photonics layer. Regional network or outer core rings will use new SDH equipment from the MSH 51, 64 and 86 range. Gateway nodes containing cross-connects for routing and traffic grooming will link the inner and outer core. National traffic is consolidated into 2.5 gigabits demands by the MSH 86 switches and routed through the optical layer to remote MSH 86 switches. Traffic at VC4, 16C and above will use a direct connection to the photonics ring. The narrowband layer. The existing mesh network or narrowband layer will be retained, but with improvements for the delivery of VC4 connections. In this section of the video, we have looked at the outline of the new ultra-broadband network. New equipment. In order to redesign the network, new equipment and practices have been used to improve capacity and to allow better use of the existing network. A ring-based architecture will still be utilised to provide resilience in the event of network failures, as well as for upgrading the network, thus enabling BT to respond to problems or increase demand quickly and efficiently. The new equipment employed in the new network will use optical technology to increase bit rate and enhance fibre usage. The new equipment and proposed uses will be the photonics line terminal PLT40, a point-to-point dense wave division multiplexing line system to link cities or DWDM rings, the photonics multiplexer add-drop PMA32, a dense wave division multiplexing optical add-drop multiplexer providing a high-capacity ring between cities. MSH 86, a digital cross-connect switch providing reconfiguration, cross-connection, grooming and consolidation. MSH 64, an SDH add-drop multiplexer with a line rate of STM64 or 10 gigabits, providing a ring for the collection services such as DSLAM traffic, DSLAM being Digital Subscriber Line Access Multiplexer. MSH 51. These are add-drop multiplexers with a bit rate of STM16, allowing customers a high bit rate connection direct to the collector ring. An element manager will control all this equipment, the Marconi MB38 and MB36 as currently used for managing the MSH 64. New equipment descriptions. Having identified the new types of equipment that will be used, let us now have a closer look at them. They will be supplied from Marconi's range of smart photonic equipment. The photonics line terminal PLT40. Marconi's point-to-point DWDM system, the PLT40, will be used. This will provide 40 point-to-point wavelengths at 10 gigabit routed over a single pair of fibres. These line systems can be used for distances of up to 450 kilometres. It will also be used where high volumes of traffic from point to point will make it cost-effective, for example, London to Birmingham. The PLT40 comprises core shelf with the line connections, extension shells that contain up to 16 2.5 gig or 8 10 gig unprotected transponders. The core shelf is a dual height shelf. The upper part contains the fan power units and the transmit amplifier which feed the signal to line. The fans are located between the shelf units. The lower part of the shelf contains the cards that handle the receive signal, a variable attenuator to condition the receive optical signal, dispersion compensators, and amplifiers to feed the signal to the extension shelves. An optical supervisory channel, or OSC, will also be combined with the transmit signal and extracted from the receive signal to provide monitoring and control via the hub and control cards which are linked to the management system. A booster amplifier is also fitted in this shelf. The extension shelves are again dual shelves with fan units between them. The upper part of the shelf contains optical connections for the transponders that are housed in either the upper or lower extension rack units. A shelf will contain 8 unprotected transponders at 10 gigabits or 16 unprotected transponders at 2.5 gigabits. This allows for up to 8 wavelengths per shelf to be carried. The transponders are provided according to the wavelength required. The multiplexer and demultiplexer cards, seen here on the left of the shelf, combine the inputs from the transponders to give an aggregate signal for connecting to the core shelf. Signals from other extension racks can be added to these cards to build up the full 40 wavelengths. A fully loaded PLT40 with 10 gigabits transponders will have 400 gigabits of traffic on the line fibres. This is equivalent to approximately 4,800,000 telephone calls. Up to 20 racks will be required for a fully equipped 10 gig system, 16 equipment racks and 4 racks for ancillary connections. This will allow for 40 channels or wavelengths to be transmitted over the line system. Initial provision capacity will be 40 gigabits in total. This will be increased as traffic grows. Each rack will have connection to a common LAN for management, using a 10 base T Ethernet to connect to the remote management system. Only one system network element identifier, or SNEID, will be required for all the racks in the PLT40. The Photonics Multiplexer Add-Drop PMA32. The broadband DWDM layer will employ Marconi's PMA32. This is a 32 wavelength optical dense wave division multiplexer. It will provide add-drop rings of about 450 kilometers in circumference and allow for high volumes of traffic at 10 gigabits per wavelength. It is provided in multiple racks. The system comprises a core rack seen here on the right and a number of extension racks. Here is one to the left. A core rack contains a main processing unit, line cards west and east, which transport the combined wavelengths around the ring, and a master and slave 32 wavelength add-drop unit to handle the signals from each tributary. A fully utilised PMA32 will be able to carry 320 gigabits of traffic in each direction over a single pair of fibres. On the extension rack, inputs or tributaries are connected via optical transponders to convert broad or grey wavelengths. It will hold up to 16 unprotected transponders per extension shelf. This will give up to a maximum of 32 inputs at bit rates of 2.5 gigs with 3 extension subracks, or 10 gigs with 6 extension subracks. The shelves are interconnected using 6 8-fibre links per rack. Each shelf also has control and monitoring interfaces for remote configuration and fault reporting. These are connected with electrical links between the racks, so the core and extension racks function as one unit and is seen as such by the management system. MSH86. The MSH86 is a cross-connect switch comprising of multiple racks. These racks contain common control and timing equipment plus switch matrices which are connected to the port shelves. The interfaces can be electrical with 4 STM1 connections at 155 megabits to each card, optical connections at STM1 at 155 megabits to STM16 at 2.5 gigs. They can be used to allow for interconnection to the DWDM layer or to the MSH64 systems. The connections allow consolidation of regional traffic for routing through the DWDM layer or for national routing, and radically reduce the need for multiple coaxial connections. This will allow the MSH86 to groom VC4 circuits between multiple MSH64s or interconnect DWDM systems. Each shelf also contains alarm and control interfaces, providing local indications and remote management. MSH64. Another equipment deployed in the new broadband and outer core will be the MSH64. It will provide regional circuit interconnection. Again, this equipment will be interconnected in a ring structure with east and west line cards. A line bitrate of STM16 will allow interconnection with the DWDM inner core. These add-drop multiplexers will accept STM1 electrical tributaries or STM1, 4 and 16 optical tributaries. They have a switching capability to provide protection and routing options. Marconi's element managers will control the network layer using the MB38 at nominated BT control centres, and with MB36s managing the individual network elements. The MB36s will manage the whole range of UBB network elements. The existing mesh network will continue to grow and be used for circuits of STM1 and below. In this section we have looked at the new equipment that will be employed in the UBB network. We'll now move on to look at protection. Protection. As in the existing mesh network, the facility to protect circuits is required. Again, a radical approach has been taken. If we consider providing protection on a 1+1 basis, every circuit will need to be provided with a duplicate route. This means that the traffic capacity is reduced by 50%. Consequently, in the DWDM layer, 1+1 will be created by the use of dedicated fibre links on point-to-point DWDM or wavelength protection on DWDM rings. Using 1+1 protection in this example ring, a maximum of 4 circuits can be carried. In the MSH64 rings, shared protection rings or springs will provide protection. This will allow for more efficient use of the equipment. In cases where specified paths are used to provide protection, as in the springs application, the circuits will be protected by redirecting the traffic onto specified protection paths within the rings. Protection can then be achieved by usage of only 25% of the ring capacity. Using springs on our example ring, 8 working circuits can be carried. And finally, another advantage of the ultra-broadband network is that it will allow specific platforms to be delivered, each using their own wavelength. This means that services such as ATM, IP, and SDH direct to customers can all be delivered using a wavelength over the DWDM layer for that platform. In this section we have looked at the new practices that will be employed within the new broadband network. Please now stop the video, rewind and read the supporting workbook, DLT 102324. Thank you.